All right, so if we take a look, ground state, excited state, and possible configurations. So we normally say that the electron configurations that we are talking about are in the ground state. Let's say you have a hydrogen. It would be 1s1. But what can happen is that the electron can get energy and jump further away from the nucleus and occupy an orbital higher than it should. This can be energy it gained from like light, for example, like solar cell, energy from fire, anything like that, or electricity, like the lights we saw earlier in the week. And here's the thing, as it jumps up, it occupies a space that's further away from the nucleus, but it can't stay there forever. It's going to end up going back down to its ground state, or its lowest possible energy. So what it will do is it will release that energy in the form of a photon, basically an electromagnetic wave. It emits that, and then it drops back down to ground state. Now, the wavelength of that electromagnetic radiation depends on which one it's dropping down to. If it's an electron that's dropping back down to the first principal energy level, then it emits UV radiation. If it's one in the visible light spectrum, then it emits if it's dropping down to the second principal energy level, that's visible light. And then if it's dropping down to the third principal energy level, that would be an infrared. So that actually determines the what you would call the wavelengths of those lights and what we actually, the way we're able to perceive them. Now, this happens when fireworks go off and the metal burns. It emits a certain particular set of wavelengths. We perceive all of those wavelengths from the individual ones jumping as a color. So just keep that in mind. So heat, radiation, even electricity, when it happens, these electrons move to higher energy levels, what we call their excited state. How can you tell if an electron configuration is an excited state? Well, everything about that electron configuration works, except you have a break. You have one that's higher or something than it should be. So let's take a look. Determine the number of electrons described by each of the following electron configurations. 2, 4, 10, 11. 1s2, 2s2, 2p6, 3p1. So this is 11, so this is sodium still. The problem is it should go 1s2, 2s2, 2p6, 3s1. It doesn't. That means that this electron is excited. So we will put excited state over here. 1s2, 2s1, 2p4. But this should go 1s2, 2s2, 2p3. But one of these electrons from the nitrogen atom here is excited. That's it. If they all match up, then it's ground state, and so on. And what if somebody showed you something at you, is like, they're like, it's just excited. And you're like, no, it's not just excited. You cannot have that. How do you know? Well, it's like somebody saying, well, it's in the 1d orbital. The first principal energy level only has an s sublevel. So it can't be in a 1d orbital. And that's what you're looking for. They give the examples, 2f or 4k. So let's take a look. 1s2, 2s3, 2p4. Well, you can't have 2s3 because there's only one orbital in s, and it can only hold one electron. So that is impossible. How about this? 2s2, 2p6, 3s2, 3p1. Well, we just have some excited electrons there. And I'll let you do the other two on your own. So that's ground state. Pretty simple, straightforward. Let's take a look at the alternate ways to present the electron configuration which I don't like, but you'll see it in books. So basically, one way to do it is to take 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p3, and basically kind of put them in their numbers. One thing I don't like about this is that the 4s actually comes before the 3d, so that can be a little bit confusing. The good thing about it is if somebody were to do this way, you can see quickly, well, the fourth principal energy level is the highest energy level. So how many valence electrons do I have there? 5 valence electrons. You can see that almost immediately. I don't like it, but I'll do it. Cobalt, 1s2, 2s, 2p6, 3s, 2p6, the 7, 4s2. Let me show you. So if somebody looks at this quickly, they see the 4s2. That's good. That tells them it has 2 valence electrons. But the problem is if they're trying to just use the periodic table to just quickly look and say, oh, well, that's this element here, then they're in for a big surprise. 4s2 element is calcium. The problem is that we've got some hidden D here, right? So it's actually 4s2 d7. 1, 2, 3, 4, 5, 6, 7. So this is cobalt. Let me show you the best way to find out what element you're talking about, and that's by knowing the total number of electrons. 2 plus 2 plus 6 is 10. 2 plus 6 plus 2 is 10. 27. 27. That's cobalt. So just keep that in mind. So you can try these. I don't like it. You might see it in a reading. That's why I do it, right? I do like this. This is the abbreviated electron configuration. This is pretty easy. So if we take, for example, the configuration of barium is this, right? Well, here's barium. Here's barium. Right here. If we go back, 1, 2, that's a noble gas. This is usually called the shortened or noble gas electron configuration. That's a xenon, and it is stable. If you're talking about xenon, you know it has 54 electrons. This is the electron configuration for xenon. This is the electron configuration for xenon. That's a lock. It's 54 electrons. So we can put brackets around the noble gas xenon's atomic symbol, and we can actually start from right there. This is on lockdown. That means that the 5th principal energy level is full. We are ready to move on. Well, I shouldn't say that, because the 5s and 5p are full. We are ready to move on, and we start right here at 6s2. That's what that does. So let's take a look. Argon, 4s2, 3d8. And here's the cool thing. If I know how many electrons argon has, by looking at the periodic table, it's 18. 18 plus 2 is 20, plus 8 is 28. That is none other than nickel. That's none other than nickel. The only thing that can be a little bit hard is if you take a look here. You need to count these up. This is why, because something's excited here. So if you just went, oh, 3d10, that's easy, boom. No, you just messed up. You need to make sure that you count argon, 18 plus 1 plus 10. Cool. I think that you can complete pages, remember I numbered these. I numbered them 10 and 11. I think you have the ability to complete that for review. That does not take us into the F, which is the first thing that we will do. Oh, I think you'll be able to figure 18 out. But it does not take us into the F too much, which means that we will be able to go into the F. Hopefully you've got the regular down to D configurations down. We'll go into F after Thanksgiving break. That'll take about half a period, hopefully. And then we'll move on to the wave math. Have a great day, and take care.